My second trick is to use something called force, momentum and force as inputs. In other words, I want to just have the first and second order differences of all the inputs as new input into the model itself. So the idea is that by putting the first and second order differences, you can detect movement and rate of change, and you can actually cluster a lot better. And this also happens to help to reduce lag. You have to use both first and second order differences and not just the momentum alone. All right. So I define them quite simply. I don't, because my data is normalized and I know the differences are okay. So the momentum is just the x at some time t minus the x at t minus h, where h is your lead time, and the same similar for force. It's just the second order difference. Okay, some people like to divide by the x's. I feel that that introduces or creates outliers, especially if your x's are small or near zero. Okay. All right, so let's just look at the results of doing something like this. Let me just close this up. And go to your force. So I've got my network, my pre. So the network remains the same. I've not made any changes at all. It's again the okay. I didn't talk about the network just now, so let me just go through it very briefly. So this part here is the training part, and it does the training. I've got two inputs, the training data and the testing data. Column 1 is my y, column 2 is my y naught, and 3 onwards, this is variable, would be my inputs xs into the model itself. I'm actually shoving this into a network function. And the network function has got 1, 2, 3, 4 layers. So I've used a 4-layer network with one linear combiner with one output here at the top. I'm sure you guys can see this or not. It's a bit small. Okay. All right, so it's got one output at the top, and I'm being quite gentle. I'm using a 2/3 shrinking at each level. If you shrink too aggressively, sometimes that causes it not to train well. Okay. And for my perceptrons, I've defined them as an inner product, which includes a bias and a ReLU as my saturator. And I've got the dropout layers defined as well. This dropout probability is defined in my config. All right, so I've used 0.1, 10% dropouts. Okay, now I've started an NN size. That means the bottom layer here on the network. This NN size here, this is the bottom layer of the network. This is the top layer of the network, is 64. Okay, so with a large-ish, this is actually considered large for, I know for image processing, you use much bigger networks. But for forecasting, you typically use smaller size networks, and you use dropouts pretty heavily, right? So, okay, my input size has changed. This number here is now 33. I've just done a calculation just to make things go right. So, this is my inputs. I've got my A5, which is my labels. This is my Y naught. Okay, and then here I've made the difference as inputs. Then I've used I've used just the basic differences, and I've used the momentum and the force. All right, so they're just defined accordingly. Okay, nothing too fancy. All right, so let's look at the losses that we get from this. Okay, and they look a little better. Okay, so previously, you recall, there was some learning here in a flat line, but now that learning has extended by quite a bit, and you've gone further. Okay, a lot of the variability here is just caused by the dropouts. Okay, and my the minimum value is 0.45, right? You'd also want to pay attention to how far that minimum value is from your mean. So I also want to just display the mean minus min over the SD, right? To just show you how much of an outlier is that. Okay, so ideally you want this number to be smaller so that it's more likely, more probable for you to get a good answer. If this number is too big, it means that you have to actually, it's an unlikely value. It's quite far away from the mean of your tests. These are all just 30 repeats, right? Okay. Now let's look at the predictions from this thing. Let's see if it's improved things or not. Okay, so again, this looks not too bad. It's fooled out. It's also it's missing the peaks though on the training side, right? So, but on the test side, you can see it's not too bad. It's forecast here correctly. There's some lag here for the minima, but it's got the general trend correct. But this part here is a bit laggy, and I think this contributes a lot to the lag, right? This part here. The problem is that this test data set is too short. I think 64 values is already way too short. You want to run something that's bigger. I purposely used a small data set because to make it feasible to run this and to run a lot of experiments. Otherwise, it take a lot of time. Okay, so let's look at the lag graphs. So look at the lag graphs now. Okay, so here you see what's typical. You've got a peak around a 0 for the training, but you have this peak for the training as well. That's really because we've used dropouts. And the peak for your test remains high, but you have now a distinct peak here at 0, right? So this is what we're trying to encourage and we're trying to build up as we go. Now, it may not be possible in this scenario, in this case, to make this really good because we're only using one input, which is the time series data itself, right? To be really predictive, there's only so much that history from your current measurements can tell you. To be predictive, you want to look at other variables or perhaps data collected from a different location, especially if you're dealing with spatial data like weather data or perhaps even demand data and so on, right? Because that can also be spatially correlated, right? So for example, let's say you've got you're trying to forecast demand for energy demand in the US. Okay, let's say your results, your station is somewhere in I don't know, let's say Florida. Okay, and if your data is just in Florida, you won't get a good prediction. But if you include, let's say, data points, let's say for temperature, etc., further towards the west, because the weather always comes in from the west, then you'll get additional data which can actually make this go right down and this go right up. Okay. So we have also like we ran in fact a competition this was late last year, December last year, before COVID broke out. And we wrapped up in January where the contestants actually try to forecast dengue in Singapore. And they use a lot of weather stations in Singapore, plus the dengue cases, not just the dengue data alone. Okay, so that's that. So let's look at the scoreboard always. So the difference got us 0.49. This gives us 0.45. Now, obviously, these numbers will change. The question is, how likely is it to change? So if you have momentum and force, generally speaking, you will definitely get a better result.